So you may or may not be familiar with things like oxidation. Stop me if you've heard this before.
Oh, stop.
Things like oxidation and oxidation state or the oxidation process. And so when you're first introduced to those concepts, they might be a little confusing. So we wanted to develop a demonstration that, I'm just laughing because you guys, Grandpa's heard this 4 times now.
But not us. Yeah.
So we wanted to develop a demonstration that showcases the oxidation process, and we wanted to make sure it was safe, cheap, and the things you would need would be readily available. And so we focused on an iron supplement tablet. They're safe, hopefully, they're cheap, and you can pick them up at a variety of stores. And so the active ingredient in an iron supplement tablet is iron 2 sulfate heptahydrate. And the heptahydrate is just how many waters are near an iron atom, and it's negligible for this research. And so here's a supplement tablet, and we can see that it's not magnetic. There's no attraction. And so the technical way to describe that attraction is magnetic susceptibility. And magnetic susceptibility is just how attractive is a certain material when it's in a magnetic field or next to a magnet. And so we can see that the magnetic susceptibility of iron 2 sulfate is 0.4 on this scale. It's almost 0. And so iron 2 sulfate is actually a good source of iron 2 ions, and so which are readily available to be oxidized to iron 3 ions, iron in its 3+ oxidation state. And so if we oxidize about 2/3 of those iron 2 ions to iron 3 ions, we get a compound called magnetite. And we can see already that although it has a large range, magnetite's magnetic susceptibility is already about 100 times stronger than iron 2 sulfate. And if we further oxidize the rest of those iron 2 ions, so we would have all iron 3 ions, we can either get hematite or maghemite. So they're all iron 3 ions. It's just the structure and the geometry of the atomic crystal is different, which leads to very different magnetic properties, because we can see here hematite has a low magnetic susceptibility. It's not really magnetic, while maghemite is on the same scale as magnetite. So some research objectives that we focused on, we wanted to develop this demonstration, and we wanted to use readily observed phenomena such as color and magnetism to showcase the oxidation process. Because we can see that with increased oxidation, we want to be able to take advantage of those different magnetic properties. We also wanted to see if the chemistry of iron 2 sulfate differed from when it's in the tablet versus when it's just the pure salt in a powdery form. And if we were making a magnetic product, we wanted to see what environment yielded the most magnetic product and what that magnetic product would be, because we can see we have 2 options. So there's several ways you can oxidize an iron 2+ ion to its iron 3+ oxidation state, and all that is the iron 2+ ion is just losing an electron. So you lose an electron, it goes to fusion. And so the way that we focused on was to use heat, because it's readily available through a propane torch, an oven, it's cheap, and it's relatively safe. It's not using any harsh chemicals to oxidize the iron. So we tried 2 different ways. We tried a propane torch and we tried a muffle furnace. And the propane torch can get a lot hotter than the furnace. So with the propane torch, we heated our samples from anywhere between 0 and 180 seconds, whereas the furnace, we heated them between 0 and 300 seconds. So one other factor we wanted to look at was the geometry of our sample, because right now the tablets are in that tablet form, and we wanted to see if they were crushed up like the just iron 2 sulfate salt, if in that powdery form, if that had any difference of the magnetic product. So the samples we tested were the supplement tablet, just iron 2 sulfate and starch, and a crushed supplement tablet. And so it's well known that if you heat just iron 2 sulfate, that it goes straight to hematite. It goes to that non-magnetic iron 3 oxide. And so some preliminary results we can see here is just like an iron supplement tablet, and with increased heating it goes to a dark brown color to an either red or a purplish gray color. So we can use that color as a gauge of the oxidation. So after we ran all these different trials of the furnace and the propane torch, we needed a way to measure that magnetic susceptibility. And so there was a way we found that we placed two styrofoam cups on top of each other, place a strong magnet on top of that, and place it on a balance. And then if we zero that balance out so it thinks it has no weight on it, as we can see here.
Well, that's the picture there with the styrofoam cups.
Yeah. So we would measure the mass of our sample, and then we would take our sample and we would put it on top of the draft door about an inch away from the magnet. And if our sample's magnetic, there'll be an attraction between the two and they'll want to move closer together. However, the sample is on that draft door, so it's not going to go anywhere. So the magnet will actually be lifted up a little bit, that the scale will be able to measure that difference and will actually read it as a negative reading.
Oh.
So then, to get the true magnetic susceptibility, we would take the absolute value of that scale reading, because we want positive numbers, and we would divide it by the mass to get the true magnetic susceptibility. So after doing that about 400 or 500 times, which was very fun, and not at all frustrating, we were finally able to see our results. And we can see through all the graphs that there's a little bit, it peaks and then it decreases. And if we see here, this is just the iron 2 sulfate. We see the peak, but if we look at the scale, it peaks around 0.12 to 0.16. And if we look at all the other trials, they peak between 12 and 16, which is about a 1,000%. They're 1,000% more magnetic. So clearly something in the tablet is making the iron 2 sulfate go to this magnetic product. So here we have the tablets and we can see that they are a lot more magnetic than just the iron 2 sulfate. And then whatever isn't iron 2 sulfate in the tablet, it's a cellulose gel, and cellulose is very similar to starch, or potato starch. So then we mixed just the iron 2 sulfate starch with potato starch, and we ran that as a trial. And we can see that it's as magnetic, if not a little bit more magnetic, than the tablet would produce. So that would confirm for us that it's the cellulose gel or the starch-like material with the iron 2 sulfate that yields this magnetic product. And so one other factor that we wanted to test was the geometry. So we have we did a crushed up tablet, the iron 2 sulfate and starch, and we can see right here, the red and green, that they follow almost the same magnetic susceptibility trajectory. They peak at the same points and then they both decrease at about the same time. And then in the yellow, we have a tablet, and we see that they have about the same peak strength, but it just peaks a little bit later. And we can also see that the iron 2 sulfate and starch produced a more magnetic material than the tablet. So after we were able to show that we had a magnetic product, we wanted to see, is it magnetite or maghemite, which is what I've been working on the past 8 months.
Trying to identify which it is.
Yeah, which one it is. And so we used a technique called X-ray diffraction. And what X-ray diffraction does is you take your sample, you shine X-rays at it, and then it gives you a corresponding intensity pattern or diffraction pattern. And so every compounded element has a unique diffraction pattern, except magnetite and maghemite. They are almost identical. They're virtually the same. So we actually found a paper that says if you look at the angle 57 degrees when you shine X-rays at it, that magnetite has a peak at 57 degrees and maghemite has a peak at 57.3 degrees.
Oh my.
And there's a few other peaks that are a little off like that, but we focused on the 57. So we needed to make sure that that minute shift was natural, and it wasn't human error or from the our instrument that we were using. And so the way to overcome that was we would spike all of our samples with an internal standard, which we used as silicon. And so we would know where our internal standard peaks are. And then we would be able to, between each trial, we would be able to line up those internal standard peaks, which would account for or overcome any possible human error or instrument error. And so once we do that, then we can look at the 57-degree range. And so here we see our internal standard peaks are all aligned. We have magnetite in blue at 57 degrees and maghemite in red at 57.3 degrees. And when we ran our sample with our internal standard, we can actually see that it has a peak at 57.3 degrees, therefore confirming that maghemite is our magnetic product, not magnetite.
How far into the research were you when you found that paper? From the beginning? Did you know that from the beginning?
No, maybe about, oh boy, I don't know, 6 or 7 months.
Oh.
Yeah, it was a while.
So you weren't,
So
you didn't have a good way to know for sure.
Yeah, I was starting to think that X-ray diffraction wasn't going to work. And so we found this paper, and actually it didn't just occur to me to do that at first. I tried several different methods, and then my professor and I just went, oh wait, let's just do this, and it worked. And so we confirmed that it was maghemite, and here we just have 2 different runs, one of a supplement tablet at 700 degrees, and one of iron 2 sulfate and starch at 700 degrees. And we can see in the very beginning, these peaks are your iron 2 sulfate with a certain amount of waters around it. And then we heat it, and it loses all those peaks, and we get the maghemite peaks, and then with further input of heat, we get hematite. These are our hematites. I actually have another demonstration. So here is, so this is the sample that was confirmed to be maghemite. And so we saw that the supplement tablet wasn't magnetic, and then we have...
Wow.
Mm-hmm.
Painted magnetic.
Yeah.
Oh my gosh. It's like that little picture guy. What is it?
That's the
Etch-a-sketch.
reference
That
that
was the
everybody...
original supplement, right? That heated
Everybody
and
says it's like my
directed
Etch-a-Sketch.
Yeah,
Yeah.
everybody says, wow, it's just like the mustache.
guy.
Yeah.
Yes,
And
yes.
so we go from this non-magnetic material to magnetic material,
Wow.
which is maghemite. And then and then we see that the X-ray diffraction says we have hematite, which we can see is not magnetic. And then this is the 300-second one. We can see that it's not magnetic as well. So we have this sweet spot of a magnetic.
Those two things, the two dark ones are different things. One's maghemite, one's magnetite.
Yep. Or no, one's maghemite, one's hematite.
One's hematite.
So
One's magnetic and one's not.
Yeah.
Oh, I see.
So let's see.
Yeah. Yeah.
One sticks, one doesn't.
Right.
And if you guys want to play with this, I can. I have a lot of fun just walking it back and forth. So after we were able to confirm it was maghemite, we moved on to this program called Rietveld refinement. And Rietveld refinement can do 2 things. It can confirm what's in your sample, and it can give you a quantitative analysis. It's 10% hematite, 15% maghemite, and so forth. And so what Rietveld refinement does is it takes your experimental data from the X-ray diffractometer, and it takes what you think is in it. It takes all that data, and it fits a calculated curve to your experimental data. So the experimental data is the red, and then if you're able to see, there's a black line in the red, which is the calculated curve. And then the difference between their two is the blue line. So the better the fit, they'll have about equal values, and when you take their difference, it'll be 0, which is a flat blue line. So the flatter the blue line, the better the fit. And Rietveld refinement can also be, how good a Rietveld refinement can also be based off of chi-squared. value around 2 is a good chi-squared. And so I've managed to achieve a chi-squared of 2.7 and 1.73. So we were able to show that maghemite and hematite and a few other compounds that I didn't expect to be present were present. So we were able to develop this oxidation demonstration. We have a stepwise manner of how you would perform it. We were able to confirm and make this magnetic product and confirm that it's maghemite. And so with maghemite, we did exactly what we wanted to do. We started with iron 2 ions and we went to all iron 3 ions with maghemite. So let me just break this out again. So with a visual confirmation, we're seeing 2 different oxidation states of iron right here with this with the input of the magnet. Here we have all iron 2 plus ions, and here we have all iron 3 plus ions, and we can see. And oxidation.
The powder started as a tablet.
This started as a tablet, and so
That was a question, not a statement. Correct?
yes,
It did. Okay.
I have a tablet. And so oxidation won't make something magnetic. It won't always make something magnetic, but it happens to in our case of iron, so we're able to take advantage of that magnetic product. So like I said, we were able to develop this demonstration, safe, relatively cheap, easily accessible tools. So we were able to confirm that it's maghemite, and the oven was our environment that produced the most magnetic product, and we saw that the geometry doesn't really affect the outcome of the magnetic. So just some future work would be, why is it maghemite that we're forming? Why not magnetite? Why not hematite? Why are we what does the starch have to do with giving us this magnetic? So that'd be
If you didn't use the starch, would you know whether you end up with the same thing? Could you do it
Yes.
without the starch and end up with the same thing?
No. So here is just without starch, the iron 2 sulfate, and it's about